Example 2, you try. So what I want you guys to try to do on your own right now is solve this problem. A spherical balloon is inflated with helium at a rate of 100 pi feet squared per minute. How fast is the balloon's radius increasing when the radius is 5 feet? So what we want to do here is take a balloon that we're filling up with air and it's getting larger at a certain rate. We want to know how fast is the radius changing when the radius is 5 feet. So let's first visualize the problem and figure out what's going on here. So here's my balloon, here's my spherical balloon, and as the radius gets larger, the balloon gets larger. And as the radius gets smaller, the balloon gets smaller. That makes sense. So I can actually visualize this in 2D in this circle right here. So as my radius gets small, the balloon gets small, and as the radius gets large, my balloon is getting larger. So right now, try to use this to solve this problem. Okay, let's see how far we got. So the first step is to identify the goal of the problem. And the goal is to find the rate of change of the radius. So to find the rate of change of the radius at a certain point. Well, this means dr dt, the rate of change of the radius. So it always helps to draw a diagram. So here's my diagram, and I know that at a specific point, r is 5 feet. So if you want to draw it in 3D, you just draw these little things. And that shows that it's in 3D now. And we're given certain pieces of information. We're given that r is equal to 5 feet. And we're given that dr dt, sorry, not dr dt, dv dt is 100 pi. So again, this is the radius, and this is the rate of change of the volume. We also need to know a formula to relate volume and r. Well, we know the volume of a sphere is 4/3 pi r cubed. So if you were not able to solve before, go ahead and pause the video and try to solve it now on your own given this equation. Okay? Let's see how far we got. So this is the solving portion. So we have that v is equal to 4/3 pi r cubed. So we want to take the derivative of both sides with respect to t. So this is going to be the derivative of v, then is dv dt, because the derivative of v is 1, and then you got to use implicit differentiation, equals 4/3 pi times the derivative of r cubed is 3r squared times dr dt, because we're taking the derivative with respect to t. Now we just need to do some simplifying. We get dv dt is equal to, these 3's are going to cancel, 4 pi r squared dr dt. Now what was the goal of the problem? The goal of the problem was to determine dr dt. How fast is the radius changing? So that's our goal. So now let's plug in information that we know. And we know dv dt is 100 pi. And we know at the second that we're going to have r is 5 dr dt. So we get 100 pi is equal to 100 pi dr dt. We divide both sides by 100 pi, and we get dr dt is equal to 1. Don't forget to include units, so dr/dt is 1 foot per minute. Radius is in the first dimension. So now all we need to do is write our answer like a sentence. The balloon's radius is changing, and a better word than changing would be increasing, because it's getting larger, at 1 foot per minute when the radius is 5 feet. Because the radius gets larger faster when it's small and gets larger slower when it's very large. And I'll show you that in a second. So what I mean by what I just said is that when the radius is small, if I animate this, it gets larger faster, so it's increasing larger, it's getting larger quicker than when it's very large. Even though the radius is increasing at the same time, the volume is increasing at a different amount. Since the volume is increasing at the same time, the radius has to change at a different amount.